Okay, here we are on page 2, and we're going to have another problem where we're going to use upper and lower rectangles to calculate the area of a shape. And it just so happens that calculating the area of the shape is actually calculating an approximation of pi, because if you have a radius 2 circle and you take a quarter of it, that happens to be equal to pi. Okay, here's the calculation to show that it should be equal to pi. So if we calculate the area of this circle, this quarter circle, we are going to calculate an approximation of pi. So it says, hey, can you get as close as Archimedes got? Okay, which is, this is his approximation. So basically what we're going to do is we're going to range from 0 to 2 on the x-axis, okay, and then we're going to use this y value to make our rectangles, okay. And so first we'll do upper rectangles, and the upper rectangles, the first rectangle is going to be like that size, right, and then each one is going to be progressively lower. So let's see, we're going to start with n equals 10. So with n equals 10, the width of this rectangle happens to be 1/10, right? And then, well, actually it's not 1/10, it would be it would be 2/10, right? Because we divide 2 into 10 sections, so that would be 2/10. Okay. And then the height of the rectangle, we would use this formula here, so it would be square root of 4 minus 0 squared, right? And which would just be 2, okay? And every time we move over, we're going to move over 2/10, and then we're going to redo the y formula. So the second time it's going to be 4 minus 2/10 squared, and the next one's going to be 4 minus 3/10 squared, 4/10 squared, right? So it's going to be 0, 2, 4. So we're going to step through 0, 2, 4 all the way to 8. I think it's going to be the last one. Is that right? No, it's going to be, the last one's going to be 18, because we want to go all the way to almost 2. It's going to go from 0, 0.2, 0.2, 0.4, etc., all the way to 1.8. Okay? So the way we're going to do that is we're going to use n equals 10, and the counter is going to go from 0 to 1.8, or 0 to 18, and we're going to count by 2's. Count by 2's. Okay. And then for the lower, we're going to go from 0.2 to 2.0, counting by 2. So we get 2 to 20, counting by 2's. Okay, so let's try to make the equation for this one. So we're going to put second sum. Oops, I don't know how I do that. The sequence, which is ops. Okay, and so we're going to do the width, which is 2/10, and then the formula is 4 minus x divided by 10, and we're going to count by 2's. It's going to be, we're going to start with 2, we're going to count up to 18, we're going to start with 2, and then we're going to go up to 18, and we're stepping by 2's. I'm sorry, not 2 to 18, 0 to 18. 0 to 18 stepping by 2's. Okay, so our first approximation of pi, and this was upper, it would be 3.3045. Just to see what we're shooting for, we do need to like figure out what Archimedes' numbers were. So there would be 3 divided by 10 divided by 71. 10 divided by 71 happens to be 0.1408. So 3.1408, and then 1 divided by 7, which was Archimedes' upper limit, is 3.1429. Okay, so the real value is 14159. Okay, so we're trying to get closer than that. So let's go back and grab our sum sequence here. And now instead of 0 to 18, now we're going to do 2 through 20. Otherwise everything else is going to be the same. It's 2.9, that's pretty bad. 2.9045. Okay. Alright, now we're going to change to 50. So we're going to do n equals 50 now, and so the counters are going to go, in this time it's going to go from 50, so it's going to be 0, to here the width is going to be 2 divided by 50, and we're going to count from here we're going to be counting from 0 to 98, and here we're going to be counting from 2 to 100. Okay, and so like these others, we're going to be doing like 2 divided by 100. This would be 2 divided by 200. 2 divided by 1,000. This would be 2 divided by 10,000. These are the widths. And then the counters are going to be going from 0 to 198. And we're always counting by 2's here. 2 through 200. And here we're going to be going 0 to 398. 2 through 400. Okay, and let's see how far that goes. Okay, so we're going to do n equals 50. N equals 50. And so it would be 2 over 50. So we'll be counting from 0 to 98 by 2's. So we get a 3.1782. 3.1783. And then we're going to do the same thing over here, except now, now we're going to go from 2 to 100. 2 to 100, jumping by 2's. 3.0983. So we're still not as close as Archimedes was. Let's do n equals 100. N equals 100. And here we're also going to put 100. And then we're going to count from 0 to 198. 0 to 3.198. 3.1604. Right? And then let's try 2 to 100. Not 2 to 100, 2 to 200. .1204. Still not that close. Now we're going to do n equals 200. So now we're going to have 0 to 398. That number is going to go here. Now these are going to start taking a while, so now whenever they run, I'm going to just pause it so that you don't have to wait for it to come back. 3.1512. Okay, we're getting a little bit closer. Now I'm going to do 2 to 400. Oops, that was wrong. Did you see that was 408? I don't know if I can't quit out of this. Should be 400. 3.1312. You see, we're still not at Archimedes' level. Interestingly enough, when I try to go beyond to n equals 1,000 or n equals 10,000, I don't know if I'm doing it in an inefficient way, but the TI-84s I have access to and the emulator are unable to do a calculation so big. And actually, we cannot do the final two n values, and we cannot get a better estimate of pi than Archimedes. So let's move on to the next problem. Page 445. A is the area under the curve between the left boundary x equals a and the right boundary x equals b. Write the definite integral expression to find this area. So here we are. It's the definite integral from a to b of the function f of x. And this works if f of x is always bigger than 0. What letter of the alphabet is the integral symbol related to? So the integral symbol is this one here. It is related to the S, of course, probably because of summation, sum. Okay. All right. Finally, moving on to the last one here. So sketch the graph of y equals square root of x. Y equals square root of x is like a sideways parabola. So we know that it looks kind of like this, intersects 1, 1. Okay. Shade the area described by integral from 0 to 1 of square root of x. So that would just be this region here. Find the upper and lower rectangle sums for n equals 5, 10, 50, 100, and 500. And then use the information in B to find the this integral to two significant figures. Okay, so once again we're going to have to use the summation. And when we do the summation, let's figure out what we're going to do for n equals 10. So we have, or n equals 5, I'm sorry, it's the first one. So n equals 5, we're dividing this into 5 sections. So we are going to do, for the lower, we'll be doing using the value 0, 0.2, 0.4, etc., all the way to 0.8. And then for the upper, we'll be doing 0.2, 0.4, 0.6, all the way to 1.0. So the values we're going to use for the counters would be, for the lower would be 0, 1, 2, 3, 4, and the counters for the other one would be 1, 2, etc., all the way to 5, and we need to divide them by something in order to get these values, which would be divided by 5, right? So it would be something like square root divided by the counter divided by 5. And then we would multiply that times the width, which would be just 1 divided by 5. Right? So this would be our value for the area of the rectangle. So second list sum, second list sequence, and then we're going to put 1/5, and then we're going to multiply that times square root of counter divided by 5, and we're going to count from 0 to 4, counting by ones. So it would be 0.54, oops, 0.5497. And the upper, we're just going to change the counter from 0 to 4 to 1 through 5. We're going to have 0.7497. And then we're going to go back up to the lower, and then we're going to change our ends to 10. So like instead of 5 here, we're going to put 10. And instead of 5 here, we're going to put 10. And then we're going to count from 0 to 9. It's going to be the upper, 0.6105. And then we're going to do the upper, which will be counting from 1 through 10. .7105. We're converging on a value here, somewhere between 0.6 and 0.7. So for 50, we're going to change our 10s to 50. And then we're going to change our counters from 0 to 49. This will be the lower, 0.6561. And then we'll do the upper, which would be 1 to 50. .6761. And then we're going to do the 100. Width. And this will also be, and we're going to count from 0 to 99, the lower. 0.6615. And then we're going to count from 1 through 100. .6715, and then last one is we're going to change this to 500 now. So if we run out of memory or something. now we're going to be counting from 0 to 499. .6656. And last of all, we're going to be counting from 1 to 500. Six, six, 7, 6. So you can see that between these values we got 0.66 6, right? And this would round to 0.67. So it looks like we know that it's going to be 0.67. All right. And if you're wondering still how you get these values that we put in, remember that first what we do is we figure out what are the indexes we need to put here to calculate each of the heights. And like for example for the first one we realized we needed to count these values 0, 0.2, 0.4, 0. Blah 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 all the way to 0.8. But we can't count by decimals with the calculator. We need to count by integers. So we make a list of integers 0 through 4, and then we need to divide these integers by some number to get these decimal values. And what we're going to divide by is 5. In this case, coincidentally, it's the number of it's the n value. Okay, so then we know that for this value we can just take the integers 0 through 4 and divide by n of 5. And that's what we plug into x. Okay? And then for the upper values, instead we're going to count from 1 through 5, because instead what we want is we want to count 0.2, 0.4, etc. all the way to 1.0. Not from 0 to 0.8, we want to count from 0.2 to 1.0. So every time you increase the n's, you need to adjust the counters also.